Alright, so here we've got a problem talking about a chin-up, and we're looking at this speed versus time graph on this one. We're assuming the motion is vertical. Mass is given here in the problem. So you can take a look at the mass just right there, and as we continue on, we can start out by looking at the picture. So in this picture, we've got sort of these different sections of the motion here. There's one of them. Oops. That's not going. There's another one. And then we've got this section in the center, and they also ask at the very beginning. But we can kind of look at each of these overall. Now we can also go ahead and draw a force diagram for this person. Here's our person. Like all objects, it's just a dot. We've got a downwards force, which is going to be equal to mg, which in this case is going to be equal to 79.8 times 9.8. So let's go ahead and get a value for that. 79.8 kilograms times 9.8 newtons per kilogram tells us the weight in this case. So it's 782.04. That's our downwards force in this case. And then we need to look at our upwards force as well, because there's some sort of, you can call it an upwards force of tension or a applied force or whatever you want to call it. I'll just call this F, which is what we're trying to look for in this problem. We're looking for what is the force exerted by the chin-up bar on his body. So that's as hard as he's pulling down, the bar is pulling back up on him. If he's stationary, then we know that these two forces are going to be equal. And if not, then if he's accelerating upwards, then this upwards force is going to be larger. And if he's accelerating downwards or in a negative direction, then the weight would be larger and the applied force would be smaller. So let's go ahead and look at each of these. At the beginning, we've got to look at the slopes for each of these parts, and at time t equals 0, we're going to say that this person's speed is changing. And we've got this slope right there, which I guess if we take a look, this would be going up by 6 centimeters per second in 0.2 of a second. So if you remember, acceleration is equal to the change in velocity over the change in time. You can actually write this as a derivative definition instead, but since it's a constant slope here, we can just use the simple definition. And so at the beginning, that's going to be 6 centimeters per second over 0.2 seconds. And so if we go ahead and calculate that, that's going to be 6 over 0.2, but it's actually not 6 over 0.2, it's actually 1/100th of that, because this is in centimeters per second. So it's going to be 0.3 meters per second squared from this graph, looking at that. So this part is what we can do for this first section. We know that that's going to be equal to the acceleration. And so MA is going to be equal to the net force. And you might have gotten this value here by multiplying this acceleration by the mass of the object. So I'm going to go ahead and do that real quick. And I get 23.94 newtons as my net force. That's the net force, that is not the applied force. So that's telling us that this upwards force here is actually going to be equal to, basically it's 24 newtons more than what that is. So I can just add 24 onto this and we get 806 newtons. You might want to keep a couple more decimal places there, but there we go. The second one seems like it has the same slope, so we should get the same value again. Up at the top, the acceleration is 0, so our net force is going to be 0. You can look at the rest of that. And this one's going to have a negative net force or a downwards net force, which means that this is going to be bigger by whatever value you get there times the mass. That'll get you started on this one. And in case you want to see the answers with my numbers, here are the answers for part C and part D, looking at those. All right, good luck.